fourth example, we have x of t is equal to t raised to n u of t, where u of t is equal to 1, which is classified or also called as a step function. Now let's start evaluating our function and have the Laplace transform of this function. Now we have the Laplace transform of t raised to n u of t is equal to the improper integral of t raised to n u of t times e raised to negative st dt. And now we have a combination of two terms, and we can't evaluate it, we can't simplify it by a single function or a single term, so we will use integration technique called as integration by parts. But to simplify the steps of integration by parts, we will use the method of tabular method or the DI method or the derivative integral method. This is how it goes. We have a derivative and an integral term. We classify t raised to n as in the derivative portion and e raised to negative st in the integral portion. And now we start evaluating the derivatives and the integrals. Let's start here in the derivative section. So the derivative of t raised to n, by chain rule we have n t raised to n minus 1. The derivative it again, we put down n minus 1 and have n times n minus 1 t raised to n minus 2. And now we integrate our term e raised to negative st. We have negative 1 over s as the neutralizing factor times e raised to negative st, and integrating it again we have two negatives, so we have positive sign 1 over s squared, since there is another neutralizing factor here, and times e raised to negative st. And for our next term we have 1 over s cubed, but since it's positive and it's negative we have negative sign here, times e raised to negative st. And putting the form, we will use the tabular method. We will match the derivative and the integral part. We'll have it like this. So it's sometimes called a tic-tac-toe method, but it doesn't necessarily mean that we need 3 steps of derivatives and integrals. It just happened that we get the 3 terms of these derivatives and 2 terms of these derivatives and 3 terms of this integral, or the y double prime of this term and the third integral of this term. And now we will multiply it. By this method we multiply it each term, and simplifying this term we have negative t raised to n times e negative st over s. And don't forget to have the sign convention of this method as positive, negative, and positive. It's always an alternate operations of positive, alternate signs of positive, negative, positive. So we have this multiplied by each other. We have negative here, so we will have negative n t, or write this as n t raised to n minus 1 e raised to negative st over s squared. having multiplied these terms, we have a negative sign here, we'll have negative here, and n times n minus 1 t raised to n minus 2 e raised to negative st over s cubed, having the limits of 0 to positive infinity. Now simplifying these terms, since based from our observation, we have seen that they have a common factor of e raised to negative st, or our kernel transformation. So we factor it out as e raised to negative st and negative t raised to n over s minus n t raised to n minus 1 over s squared minus n times n minus 1 t raised to n minus 2 over s cubed. And to simplify the equation, having these limits, we let proper integral of e raised to negative st dt, we let improper integral of e raised to negative st dt equal to m for the meantime. And based from our observation, we can observe that the exponents of RT is increasing, or has a pattern of n. Since from n it becomes n minus 1 and it becomes n minus 2. And the denominator s, we can also analyze it and observe it as an increasing exponents. As we can see, it becomes s squared and it becomes s cubed. So we can have it in the form by observing the exponents of our equation, having this as n times n minus 1 times n minus 2 over, since we can summarize these terms as an increasing, as s having an increasing exponents, we can have it as s raised to n. And evaluating this integral, or evaluating our m will be equal to integration, or improper integral of e raised to negative st. So we'll have negative 1 over s e raised to negative st, limits of 0 to positive infinity. So we'll have negative 1 over s times 0 minus 1. So we'll have m is equal to 1 over s. And having our 1 over s here, we'll multiply this as 1 over s. This is our value of our m. Multiplying this, we'll have n times n minus 1 times n minus 2 over Sn plus 1, as based on our law of exponents. And simplifying this, as n in the denominator, as n increases with a certain pattern and our s here also increases, we can have the Laplace transform of t raised to n u of t as equal to n factorial over Sn plus 1. So we have the Laplace transform of t raised to n u of t is equal to the n factorial over s n plus 1. And that is our Laplace transformation.